our presentation was because it's not only a mystery to us, but humankind in general. And also, it directly relates to our course theme about how we deal with not knowing. When it comes to black holes, there's knowledge that simply just cannot be obtained. And the way that we deal with this is very much represented in the media and how they will make things up to entertain and also to fill in gaps because people are just not satisfied with knowledge.
Okay, so to start off our presentation, we investigated some of the misconceptions that people actually held. So the best way that we thought to do this was to actually take a survey of Georgia Tech students. So we took this survey with 100 students at Georgia Tech to make sure it was a uniform sample, and we asked them 16 questions. Displayed on the board and on your brochures are 8 of those questions, and they are separated into 3 categories. The first 2 questions are opinion questions, meaning there's no right or wrong answer. The second 2 questions are fact-based questions that we did not expect to be in dispute, so we expected that the average answer was closer to the correct answer. The last 4 questions we expected to be incorrect. We thought those would be misconceptions, so wherever the answer lies, the data should go to the other side. We asked our questions in a particular format to get quantified data so that we can make bar charts, and that was to give you a statement and then have you rank from 1 to 5. The first 1 being completely disagree and 5 being completely agree. We predicted that the first 2 questions would have a larger range than the other questions because the first 2 questions were opinion-based and the opinions lie on a spectrum, whereas the other questions should have had a definite answer, true or false. As you can see, our prediction there was somewhat correct for these 4 questions, but not so much for the 2 misconceptions on that side. Okay, so to follow up the Georgia Tech survey, we went and did a survey on the class. So our class survey had about 20 responses that we could use, and they were slightly more correct than the average answers for Georgia Tech. However, when I say slightly, it wasn't statistically significant, and it could be contributed to the fact that you guys have seen our proposal previously, and because some of you have reviewed our media previously. So while the scores are slightly higher, they are pretty much the exact same as the 100 Georgia Tech students.
Alright, so what I had it down to you guys earlier was just a brochure. It's a quick takeaway. It has why we believe that black holes are important and why we should research on them. Some common misconceptions about black holes and why they're false. And then also a glossary of terms. We understand that this is a very scientific-based presentation, and as we do define the terms in it, we also just thought it would be easy for you guys to be able to quickly refer to them during the presentation at any time. And on the back, like we said, we have the survey, so just so you guys can look at those in your depth. Okay, so how do we know they exist? Some people still believe that black holes do not exist, but we have scientific evidence to prove that they do. This is this equation right here represents the escape velocity that an object must go to escape a black hole, and it just shows how the matter around the black hole acts. And then this is the mass that the sun must be in order to form a black hole. Another way that we know how they form is that when a black hole passes in front of a star from our vantage point, the black hole will actually bend the light around it, making the star appear brighter to us. And this is because light goes into the black hole and it bends around it. And so we have a quick presentation to just show you how, by looking around a black hole, we can tell where it is. As you can see, there's obviously a sphere underneath the blanket, but you can't directly see it. But by looking at how the blanket around it bends and folds, you can tell that the object is there.
Another way that we know that black holes exist and we can observe them indirectly is by the emissions that radiate from them. And underneath the towel here, there's a cell phone. If Hope would give it a call. Hope or Lauren, yeah. So there's, around the black hole, there is an accretion disk of gases. And as you can see, you hear the cell phone, but you don't see it, so you know it's there. So even without actually seeing the cell phone, you know it's there because of what is coming out of it. And this is analogous to the emissions that will come out of a black hole's accretion disk, which emissions come from it due to the friction between gases being pulled in by the black hole's gravity, as you can higher energy emissions come out, and that's how we detect them.
Okay, so now that we've established that black holes do indeed exist, we're going to go through their basic structure. The basic structure of black holes derives from their gravitational strength, which is one that is so powerful that even light can escape it if it passes too closely. So if you approach a black hole, the first thing you're going to see is the accretion disk, which is that disk of extremely hot and extremely compacted gases that are slowly spiraling into the black hole. And these are also the gases that we were talking about emitting electromagnetic radiation in the form of X-rays. As you fall closer to the black hole, you will eventually be able to see the event horizon, and this is the boundary of no return. Nothing, not even light, once it passes that boundary, can return to the outside universe. And because it absorbs all light, the event horizon will appear to be a pure black circle in space. So once you pass through the event horizon, you'll approach the singularity, which is the center of the black hole and theoretically a point of infinite density and approaching zero volume. However, no one really knows what happens inside of a black hole because once you pass the event horizon, you can't come back. So in order to help you visualize black holes better, we have a short little demonstration about what they actually look like. So this here, you can tell is a circle because there's no shading on it from light or anything, it's just a 3D circle. But this looks like a sphere because you can tell that light is hitting it and casting shadows on it. Now, black holes are three-dimensional objects, but in space, they absorb all the light, so they appear to just be completely shaded in, like this. So instead of looking like a sphere, they actually look like a circle. So if you were to see a black hole from any angle, it would just look like a pure black circle in space, even though it's three-dimensional.
Okay, so one of the most common misconceptions that we found from our survey that was like misunderstood by a very large amount of people was that our sun would turn into a black hole. And this is not true because the density of the sun is not high enough for it to turn into a black hole. So what determines whether a star turns into a black hole is its density. When a star reaches the end of its lifetime span, there are multiple paths they can take after that. So it can turn into a black hole if it is dense enough. If it's not, it can turn into a white dwarf, which is formed because when the star collapses in on itself, there's a lot of electron repulsion, which prevents it from becoming a black hole. And white dwarfs have a higher more of a gravitational pull than a normal star, but it's nothing that's like extremely anything that bends space or anything like that. The other alternative is a neutron star, and this is kind of the in-between between a white dwarf and a black hole. It has a very strong gravitational pull, and it can bend space and time, but it's not as dense as a black hole. And when our sun does come to the end of its lifetime, it will turn into a white dwarf.
Okay, so because this is a very conceptual idea that Lauren just covered, we're going to do a demonstration. Tamika, come up here, please. Thank you. So in my hand, I'm holding a gigantic star. It is huge. It's also a balloon covered with tinfoil. So what I'm going to ask you to do is to try to compress this balloon. It's not very easy to do. So Tamika's our hands represent gravity pushing inwards, and the air in the balloon represents nuclear fusion going inside of the star that's pushing outwards. So every star, when it's active, has a constant battle between the forces pushing outwards and the forces going inwards. Well, at the moment, you can't push inwards, but over time, the nuclear fusion will stop, and all of the energy and gas inside of the star will dissipate. This might take a couple seconds. So after all the air has dissipated, will you try again? Just keep crushing. Keep crushing. That's good. Very much. So this is the point of singularity. So at the end of this star's life, the force of gravity pushed so hard inwards that it condensed into a solid ball. Now, it is important to mention that the force of the hands pushing inwards is the force of gravity, and the force of gravity is equal or is proportional to the mass. So only big things will have strong forces pushing inwards. And our sun is not the big thing. I know that sounds strange, but the things that will be pushed in are 3 times the size of the sun. So our sun will end here, whereas 3 times our sun is going to end black hole.
Alright, so just some common black hole behavior. Every celestial body has what's called a gravitational well around it, and this is dependent on the density of the body. So our sun, this is the graphical representation of the well that's around our sun, and then this is the graphical representation of the well that's around a black hole. As you can see, it's much stronger, and as it goes to the point of singularity, it gets much, much greater. And this is a picture of the galaxy Andromeda, and it looks like the accretion disks around a black hole, and that's because it's believed that there actually is a black hole at the center of our galaxy, and so it's slowly swirling around that.
So what exactly happens inside of a black hole? Well, scientists today, there is no consensus on what happens, but there are 2 major theories on what happens as you approach the event horizon. The first one, named spaghettification, which is a fun name in itself. The idea goes that as a particle approaches a black hole, gravity pulls harder on part of that particle that is closer and less hard on the part that's farther away, so that it's pulled into a long string, spaghetti, hence the name. And the other theory being that of the firewall, which states that as you approach the event horizon of a black hole, you are bombarded by emissions from that black hole and you burn to a crisp. So despite there not being consensus on what exactly happens, there is certainly agreement that going near a black hole, you will die. There is no way to travel through them. They will crush you. The emission that contributes to this firewall is due to a theory called Hawking radiation, which is off the principle that the more precisely you know the position of a particle, and in the case of a black hole, you know the singularity in which all the particles are, the less precisely you know the velocity. So if you know that exact singularity of all these particles, the velocity is a great unknown, and theoretically the velocity of these particles could exceed even the speed of light, and therefore escape the event horizon of the black hole and be emitted.
So now that we've gone through all these misconceptions about black holes, let's look into where they come from and how the media fuels the misconceptions. So 2 obvious industries in the media that fuel misconceptions are the movie industry and the television industry. Movies such as this, like Star Trek or Event Horizon, portray black holes in a way that is just completely incorrect. They sometimes in Hollywood don't even try to make them seem realistic in any way. And we also have a clip from The Simpsons, which is obviously a comedy television show. And it also portrays black holes in a way that's rather silly because movies and television are meant to entertain. So we have stuff.
The Large Hadron Collider, or LHC, is the most powerful particle accelerator ever built. Scientists are divided about whether or not this experiment is safe. CERN, the organization behind the LHC, acknowledges in their report that miniature black holes may be produced. If such black holes are stable, they could lead to the destruction of Earth.
So clips like that can sadly be found all over the internet, which can be a source of great information, but in this case we find things that are just untrue. That clip was taken from a website called lhcdefense.org, which is an organization that tried to take advantage of ignorant people and tried to spread false information and prevent research by the LHC, or the Large Hadron Collider. They were actually successful in filing legal injunctions against CERN